Let's continue with a very simple example. Let's say we want to produce a hash of the English letter A. Then we know that the ASCII code of A is this 011000001. Now we know the first condition is that we have to make input equal to 64 bits less than 512. Okay, so in this case, what is this? 512 minus 64, 448 bits. So how to do that? Go back to the previous video. You will see the first step is we will have to append some bits here. So we'll start that with bit 1 and then zeros. How many zeros? Number of zeros, so that the total length becomes 448 bits. So we can see that we already have this 8-bit, right? So this is the 9th bit. Now 448 minus 9, so we need to append 439 zeros like this. Now this is 448 bits. After this, what is the next step? We need to append the length of the original message. See, the length of original message is 8-bit. Okay, so what is the binary form of 8-bit? Which is 1000. But we will insert around 60, in fact 56 bits before this, or how many zeros we need to make it 64. Okay, so that this is 64. So we'll add here now 0 0 0 dot dot dot. Now 1 0 0 0. Now this becomes complete 512 bits input perfectly as per the algorithm, so that we can produce the hash using message digest 5. I repeat, what is the first part? So the first part is the 8-bit message, then a bit string starting with 1 and 0, so that the total length becomes 64 less than 512. Now we are left with 64 bits. So what is the length of original message? 8-bit. Write that in 64-bit format, starting with zeros and last bits will be the actual length. Append that here. So this is the input for our algorithm. Now this 512 bits input is equivalent to 1 block for our MD5. So instead of, suppose we have taken input as A, if instead of A the input is something very lengthy, such that the total length is more than 512, suppose 600 bits is the input, then it will become 2 blocks of 512 bits. We'll see it later. The next step is quite clear, that you have to initialize these 4 buffer values, which will be used subsequently to produce the final hash. Then what is the next step to do? This message, which is of 512 bits, we need to split it. 512 bits, we need to split it in how many parts? 16 parts, each being of 32 bits. Okay, and let's call them as M0, M1 and M15. For example, in our case, what is M0? We can easily see. So M0 here is 0 1 1 0 0 0 0 1, then 15 zeros. So we can, let's write this one: 0 1 1 0 0 0 1 1 0 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Oh, sorry, we need to take it 32 bits. So we have zeros here, continue. Yeah, so this will become 32 bits. Then similarly, maybe M1 is all zeros for this case, so on and so forth. What will be M15? If you see, M15 is the last part, and last part is what? We have all zeros preceding it, and at the end it is 1 0 0 0. So we'll write here, so 1 0 0 0, these are the 4, then 12 zeros, sorry, 28 zeros, so that it becomes 32 bit. Okay, so this is how we divide this message into 16 parts. Then we know that we need these constants ti. So how were they produced? So we will find sine of I, take absolute value of this and multiply this with 2 to the power 32. We have demonstrated this in the last class also. So this will be, this T function will actually be same for all the MD5 algorithms, starting from I is equal to 1 to 64. Now, how do we utilize these 64, these constants? So basically, we will divide them into, 4 groups. So 16 into 4 is 64. So that is what we said in the previous case. We will have 4 rounds. What does it mean? So in first round, let's say for I between 1 to 16. So for this, we will use that nonlinear function. If you recall in the previous lecture, we defined 4 different nonlinear functions which are operated on those 4 buffers, this A, B, C, D. And how will be the user? So in first round, we will use the first, that function. In second round, the second function. Let me write that again here. So here I have written it here again. Okay, sorry that I have written the small bc, so you can take it as capital BC. So in the round 1, that is when I will be between 1 to 16, that is when we will be using T1, T2 up to T16. We will take XOR between B and C, and between B and C, and then OR that with not of B, and AND that with D. So here it is, these are the 4 buffer values. I will do this operation. Then for I between 17 and 32, we will use the round 2 function, this function. Then for 33 and how much it is, so 48, we will use round 3 function. Then for I less than equal to 49 to 64, we will use round 4 function. And what we will do in each round, we will do those operations. Let me recall. We apply this BCD to this round 1 function. So in round 1, we will be using T1 to T16, and then we will apply this. So we will do B and C, then not of D, or that with this, and then again and with D. Okay, whatever is operation written here. So whatever we get the output here, we add that with whatever is in the A. Then whatever we get there, we add that with whatever is in, suppose, the message block 0 which we are operating. Then whatever we get there, we add this with this T, and we will have here the loop over this T from 1 to 16. This is round 1. Then the round 2 will repeat, but now what will change? We will have again this BCD, but the function will now be this B and D, or with C and not D. After whatever we get with this nonlinear operation, add that to A. After that, add that to message and 0, and then we will have this T operation. So we'll repeat it. So in each round, we will have 16 values of these T that are being used, and finally after 4 rounds, we will completely use these 64 T values to produce the hash. So to make it more clear, suppose we represent by F these functions which we are operating here in round 1, round 2, suppose this. So what we are providing the input B, C, D as this input. Then to this function we add first of all A, right? Then we add the message block. Let's say we index that with K. Then we add this Ti, right? And then finally, if you remember, we basically shift whatever we get at the end, right? If you recall what we did, so in previous class again, so whatever was previously in B, we shift that to C. Whatever was in C, we shift that to D. So there is nothing here. Then whatever was in D, that is shifted to A. And whatever we get after these operations is stored in B. So this we repeat for every message block, and what we get after all message blocks, the same processing is done. that 32 into 4, which is 128 bit, is produced, which is called message digest. This is the hash code of input. So in this case our input is very simple, A, but you can have input very lengthy, something A, B, C, D, E, F, G, whatever you write, then it will be done accordingly. So I hope that this example makes it a little bit clear. Let me summarize it briefly finally again. Now first step with respect to implementation will be, so you can have input as A, B, C, any letter up to Z. So the first will be the convert it into binary. Okay, the second will be padding, starting with 1, then all zeros till what point, so that the length becomes 512 but less than 64. Okay, now there is one important thing. Suppose if there are multiple blocks such that, suppose the input is of 1000 bits, then what does it mean that 512 minus 64? It will actually mean this, that we have for one block, what is 512 minus 64? It is 448, and 448 modulo 512, you know that it is 448. Now this point may not be for those who haven't understood modulo. Now if the input is very large, more than 512, what should be the length you will make? So mathematically we say that let x be that length. The length should be such that x modulo 512, this should be congruent with 448 modulo 512. It means that you have to insert these padding bits such that well, how many padding bits? The value of x should be such that if you divide x by 512, you should get the same remainder when you divide 448 by 512, that is 448. Okay, let me give one example. Suppose let's take 960. What if you divide this by 512? You will get 448. So you can say 960 modulo 512 is congruent with 448, right? So what does it mean? Now let's take some, let's say if you have input bits are there 700, fine. So how many this padding should be done? How many bits we have to add? So we have to add, what is the next number which is congruent with 448? 960. So now what is 960 minus 700? So it is 260. So it means we need to add 260 bits. 1, then all zeros, fine. So we'll have 960, and then the input is actually of 700 length. So what is the binary equivalent of 700? So in decimals it is 1010111100. This is the binary equivalent of 700, and represent this in 64 bits, that is have zeros before it, so that this becomes 64 bits. Now pad this at the end of this 960 bits plus 64, so what it becomes? 1024. Now finally we have the input for the hatching algorithm of 1024 bits, and it can be broken into 512 blocks. So this has been converted into 2 blocks of 512 bits. Now we will apply the MD5 algorithm to each of these 512 blocks in the same way, divided into 16 parts, each of the 2 bits, and all those steps will be repeated. I hope this example makes it more clear. So this is all about hashing algorithms. We will not do SHA. MD5 is the only one we will do. Okay, thank you.